Thank you, Rob. And I think you're the first person to call me a roboticist. So I normally am a materials. Thank you. I appreciate that. I finally made it. Yeah, you're my last night is my morning. So I made the unfortunate error of trying to drive there at 2 a.m., which I think is the witching hour for deer. So in any case, what I'm going to talk to you about today is embodied intelligence and a somewhat new concept called embodied energy. And I'll use soft composite materials to demonstrate that in robots. So the story arc will be embodied intelligence. This is a well-studied field or introduced by Rolf Pfeiffer. Then embodied energy, which actually is, I thought was going to be a new field until I discovered, as I always do, that somebody else did it first. The person that did this was James Thomas at the Navy. Then I'm going to talk about how 3D printing can allow us to take advantage of embodied intelligence and embodied energy. And then the last part, I'll talk about using a volumetric placement of sensors in robots for improved autonomy. So the multi-objective function I'm trying to solve in my group is endurance and adaptability for untethered autonomy. And coming at this, like I said, I haven't been called a roboticist until recently. So I had to come at this from a new perspective for me and think about what are the problems in robotics. And endurance, how long can a robot operate for, seems to be a challenge. Wheeled robots do very well, but at a high cost of just leveling the landscape. And adaptable and agile robots like Atlas, running around and doing backflips and everything, they're very agile when they actually work, but they can't do these tricks for very long before their stored energy is spent. If you use an old method, the theory of inventive problem solving, which is just a historical catalog of all the different engineering contradictions and their correlated solutions in the patent literature, you can find some ideas that can help you create solutions to this problem. So in the TRIZ matrix, one historical solution to the adaptability versus endurance contradiction is to make movable parts fixed and fixed parts movable. Then of course the creativity still has to happen. You have to figure out what that means. To Boston Dynamics, I think that it means put wheels on the feet of your legged robot, and I just think that's really cool. So that's Handle if you didn't know about it. In the field of soft robotics, a long time ago, McKibben actuators were made, and then this really famous professor in our field, Susan Mori, came up with soft actuators that look a lot like flexible borescopes. Well, in TRIZ, this was a solution to that contradiction prior to both of those inventions, and it says if an object is rigid or inflexible, make it movable or adaptive. And so that's what I would say the field of soft robotics is currently trying to do. At the same time, embodied intelligence was a field pioneered by Rolf Pfeiffer and others. But this is the idea that cognition or at least computation is assisted by the physical body that the robot operates within. So the body is an enabler of cognition. These are just the rules to embodied intelligence. Many tasks become easier if stiffness and deformability of materials are used properly. So soft materials can, in this conceptual framework, improve the intelligence of a machine automatically. It may or may not improve the computational complexity. It probably increases the computational complexity unless sensors are involved. If sensors of a robot or organism are physically positioned in the body in the right places, then you can use pre-processing, which can reduce the load on the neural system. But this is, in my opinion, a bit, you can argue this point a bit. If the material properties of an agent's muscle tendon system are exploited, rapid movements such as running can be achieved, even though the neural system would be too slow to control. So you can use tendons and ligaments. We use tendons and ligaments, for example, to automatically or autonomously respond to the environment with no central processing from our brain, which would reduce the speed in which we could react. And the last one, informative and correlated sensory signals are generated in different sensory channels. If the environment seems to flow past your eyes at the same time that the sensory of your leg muscles register the strains of moving, you can use the fusion of this sensory information, a lot of it mechanical deformation, for improved controls. Okay, so Rolf and Josh Bongard and others have been thinking about this for quite some time, and have done. And I'd say the rules for this are pretty well established. In the area of elastomeric actuators, which is primarily what I work in, we use soft actuators, but our actuators are soft and respond to the environment, not because of their shape, because of their material properties. In this video here, you can see a balloon with 6 different arms that we inflate that then wraps around this fennel to grab it and then pick it up. These balloons are deforming based on the stress strain curve, so the slope of this curve, and the integral of this curve before the rubber ruptures is its toughness, and the amount of energy that these materials can absorb are very large. You can see I'm calling it work of extension here, because if you don't rupture it and you just come up the slope and then come back down, that's called the work of extension. But the work of extension of failure can be megajoules per cubic centimeter, which is very large. When you're engineering soft robots for embodied intelligence, you can think about designing with toughness instead of strength. So the strength is the maximum stress before the material yields, which is pretty low relative to, say, steel. But the energy absorbed is quite, it depends, but can be large, especially when you consider the strain to failure. And if you were to push a piece of steel an inch, it would stay in that condition. But if you were to push a slab of rubber an inch, it would come back. The reason it comes back is due to entropy. These are entropy-driven systems, a polymer network. So you take out enthalpy from the equation, and the free energy equation, if you take the derivative of the entropy with respect to length and uniaxial direction, and you just go through this, then you get the force per extension. And if you take that force per extension by the area, then you get the stress. And that stress is related to this, is proportional to G. G is the elastic modulus, which is represented in that curve. So the material properties and its response to the environment, you can program with chemistry, where that chemistry are primarily affecting G, which is the number density of crosslinks in that elastomer network. So I just wanted to talk a little bit. That's the only thing I'm going to talk about, polymer physical chemistry, nothing else. So now that we know how we can change our rubber properties to stretch with stress, we can pattern balloons to do something more than just inflate fingers. In this work, James Peekle, who's actually now at University of Pennsylvania, showed how we can pattern fibers onto rubber sheets to inflate them into any shape we want. If you just look at this middle row, you can see a rubber sheet that we then laser cut rings and put those rings onto the rubber sheet. What these rings do is when we inflate a balloon, it normally inflates radially and circumferentially. It's very hard to predict a priori what a shape is going to be if you pattern fibers onto it or inextensible material when you're getting inflation in both of these directions. It's not hard to predict when you know you're just going to get radial projections. If you limit the circumferential expansion of these balloons using these inextensible rings, and it's something anybody can do, you can laser cut these rings and then you can just glue them onto rubber sheets. When you inflate them, you just get projections. And so then you can beforehand 3D scan an object, translate it into these projections of rings, pattern it onto this rubber surface, and then inflate it into positive, negative, and zero Gaussian curvatures, which in theory you can then use to produce any shape you want to. So now we can use balloons to make any shape we want to. We chose a low aspect ratio leafed aloe plant. And so these are ellipses we patterned onto the elastomer sheet, which we modeled as overlapping rings. This is an older video, which we actually didn't use that logical programming to create. This is just trial and error, and it's got a really dumb controller, me on the outside of the video. So it's just a machine. I'm causing it to walk to this gap, and then it'll undulate underneath the gap. I'll just skip forward. Okay, it gets to the other side, but my point of showing this here is that this is just a machine. There's no sensors built into it, and all the energy is being delivered through pneumatic compressed air outside of the robot. If we untethered it, it wouldn't work. And if we put compressed air cylinders or air compressors with battery packs on it, it either wouldn't move because that's too heavy, or it wouldn't move for long. This is an example of that. We made with Mike Tolley, made a very large, just about 1 meter long robot with a battery pack and air compressors on it that cause these legs to move. This is real time, but the prior video was sped up. And so now the car can drive over it again because it's a very tough material, but it can't operate for long because of just the configuration. I'm going to show you in a moment how we can use embodied energy, the concept of embodied energy, to improve the duration of autonomy of that. This is an example I wanted to throw in here of why these actuators can be useful. This is a haptic interface that we put onto a HTC Vive controller. You can see it moving around here. And NVIDIA changed their VR Funhouse code to output signals to a valving system we made that then changes the shape of our sleeve here, so you can feel an abstract representation of what you're doing in the game. It's not real. We just made up what people would like to feel when they're interacting in these environments. This person's boxing, but the inside of his hand is inflating. Okay, so that's all examples of what we can do with soft actuators and how they can improve, how embodied intelligence can be used for more effective interactions with simple fabrication. But again, as I pointed out, these machines, we haven't solved the endurance problem. And in fact, the pneumatic systems require pumps, and these pumps can add weight, significant amounts of weight, without improving function. So we thought, how can we improve the endurance of these soft robots? And I'm working on a project for the Air Force, and I keep on seeing all these great demonstrations by birds, avian-inspired morphing wings and things like that at these conferences I go to. And one of the most incredible things I've seen is just how long these birds can fly for, migratory birds can fly for. So this is a bar-tailed godwit that gets twice the weight, its normal weight, before it flies for a week straight across the Gulf of Mexico, I believe. And this weight is all fat. And so people, the best paper on this is calls them obese super athletes. And I think it's just really incredible. And so then that got me thinking, how can we use energy in a multifunctional way? Because they use it for thermal insulation as well as energy and probably many other things without reducing their performance significantly. And so then that got me thinking multifunctional use of energy. And then I found a paper by James Thomas, which outlined some rules for multifunctional use of batteries. In the rules he's outlined, one is add new functionality to the material with the more complex function. So the battery is more complex than an I-beam, so make the battery structural rather than the structure of battery. The The problem with that is that the battery will make a worse I-beam, but the I-beam will certainly make a worse battery. So that's the compromise you should make. Number two, target unifunctional subsystems, materials, components, operate in mid to lower functional performance regimes. So number two is acknowledging that the battery is not going to be as good. So use it in places where the performance doesn't have to be as high. And then number three, implement multifunctionality in the conceptual stage. So don't try to take a car and then just replace the door with a battery. You're gonna have to start from zero with this concept. and so there have been several people that have done something like using flexible batteries or thin batteries as the wing surface of a flapping wing. There are many other examples. One example is using a lead acid battery as counterbalance in a forklift. So this idea is very old. In this case, James Thomas and his collaborator put a flexible thin battery and replaced part of the wing of a glider, of a flyer, propeller-based aircraft. And then if you take into account the amount of mass reduced by not having a normal battery in there and replacing the weight of the wing with that battery, then it operated for, it had an energy density of 161 watt-hours per kilogram versus 136 watt-hours per kilogram. I must admit, I did forget exactly what the improvement was in this. It was something like 15% improvement in systems energy density if you read through these numbers. Okay, but what we did is, instead of using a structural component that we replaced the battery with, we replaced a soft component, or the fluid. And this idea on top was, again, from seeing these migratory birds, but I want to give you some numbers to compare. So my best estimate, this is a guess, that the Atlas may have something on the order of 20 megajoules onboard energy storage, whereas a human, like myself, I have about a gigajoule of energy storage in fat. That's for two reasons. One, fat just is more energy dense in the first place, but another reason is that it's distributed everywhere. Me more in my gut than I'd like, but generally everywhere. And so then if you add all that up, then we can operate, including, and if you take into account our just really great control system, can operate for weeks without eating. You wouldn't want to, but you could. Okay. So in the demonstration here, we took a zinc iodide flow cell battery. This is just a liquid battery. Specifically, it's a half flow cell battery. So one half is a flexible anode and electrode, and the other half is a liquid catholyte that then, when the zinc on the flexible anode is oxidized, it sends an electron through the electronics, including the pump that moves this catholyte, and then the electron goes into the iodine solution and then reduces the iodine, and then the zinc moves through a separator into the iodine solution to balance the charge. So this complex, electrochemistry, which is, well known for a long time and is used for grid energy storage and large battery systems, we moved into a very small vascular network that stores energy but also acts as a hydraulic actuating fluid in a soft robot. So James Pekel, again, he designed this lionfish-looking robot so that there's a lot of pockets to store the catholyte. So the lionfish has a lot of nooks and crannies that we can pack a lot of energy in. And then there's two pumps. There's a pectoral fin pump and a tail fin pump. These are two different actuator networks that are sharing the catholyte and are actually connected in series. So the graph on the bottom right, and we designed this from the ground up using Rule 3 of the Embodied Energy concept. And we designed it from the ground up so it would be mostly hydraulics. And in a mostly hydraulic system, that's where you really get the advantage of multifunctional use of a liquid for energy storage. So using a 124 watt hour per liter half cell battery, we managed to get a 350% increase in system's energy density if we were to use just water as the actuating fluid and a coin cell for powering the pumps and the controllers. You can think, well, that's an arbitrary thing to say because you could have just made it really big or whatever. And that's true. So we made this little diagram that shows, what kind of trade-offs you expect. If your existing machinery is 50% hydraulic fluid, which happens in hydraulic lifts, then you get, not much. You'll get 110% increase if you use a 300 watt hour per liter system, and not much at all if you're using ours. But if you are using a soft robot, which uses a lot of hydraulic fluid, then you get large gains, especially if you pump up the electrochemical energy density to 300 watt hours per liter, which is quite possible, but a little bit dangerous. So this is that fish swimming. You might notice is not going very fast, and that's something we noticed. Of course, so flow cell batteries separate the energy density from the power density. So the energy stored in these sharp little dorsal fins of the lionfish, they don't have separators and they don't have electrodes, so they're not actually contributing in powering. The battery contributes to power when it gets into the body, and so that's where the separators are, and the fins and the tail. To increase the power of this robot so it would swim faster, we would have to put separator material everywhere, or start using capacitors or electrical engineering more cleverly for high-speed maneuvers. And this is the tail moving at 3x playback, and these are the pectoral fins expanding mimicking a threatening display, which does not look that threatening in this kind of robot. I think that's all I want to say about this. Yeah. Okay, so all of that is really very little good. The actuators, the stored energy, or even the sensors I'm going to show you later, if everything is really complicated to make. So as Rob alluded to earlier, or just straight out showed, 3D printing can make really complex shapes. I think Hod Lipson was the one I heard say complexity is free. So all of these complex fabrication techniques that's required to embodied intelligence and embodied energy work really well is for naught if the cost of the robots are so high. And 3D printing is an enabling technology that allows us to get right to that. So we choose to use projection stereolithography in how we make our robots. Mostly because it's fast and high resolution. The downside to it is it's usually single material. So making the hybrid systems Rob was talking to would be very difficult to do in stereolithography. So we primarily use structural modification of a single material to change how it deforms. In this hand, which has all the power and control in the palm, we just mount it on this arm. We use small DC motors that we gear up using a passive transmission system that we print, and then we wind tendons or these Kevlar wires through the fingers, and the fingers are pleated where we want it to bend, and so that's how we get that to work. This is a schematic diagram of this hand that we printed. There are these little white pads, and these white pads behind them have time of flight sensors that let us know when an object is coming near, so then it can automatically start grasping. They also have these little rubber wheels, and these wheels are what the tendons wrap around. At no loading, in a no loading condition, they're of large diameter, and that means they can spool quickly. But because they're soft, after the fingertip of this hand touches something, it starts to apply a load to this spool, which then pulls in and allows us to apply a higher force at the end of the fingertip. So this dynamically changing spool allows our prosthetic hand to use the small motors to have high closing speed and high closing force. So it's one of the best powered prosthetics in terms of closing speed and force and weight and cost that exists. That we use a carbon M1 stereolithography printer using an elastomeric polyurethane to make those prior demonstrations. There's also a silicone polyurethane available for that system, but none of them are as soft as we would like. They're all 500 kilopascals and up, and a lot of the projects we work on, we want to use for biomedical devices that can be used in the body for surgery potentially. And so for that, we want sub 100 kilopascal elastic moduli so that we stay below the threshold of damage for a lot of our sensitive internal organs. So we came up with a Thiol-ene silicone click chemistry to print these silicones directly that have, again, very low elastic moduli. And we can tune this using the density of thiol groups and the molecular weight. So the density is represented by this 5%. 5% of the groups are cross-linked using Thiol-ene click reaction. And then this 186, 6,000, these represent the molecular weights of the polymers. And the bigger this number is, the softer it is, and the more it can stretch. And the other side of it, the higher the percentage is, the less it can stretch and the harder it is. So we have to tune between these things. But the most important part is that it is very soft, sub 100 kilopascals, and it's very resilient. So we can cycle it hundreds of times without it failing or without it even changing its stress strain profile. Using this material, we could print extremely soft actuators and figures. This video isn't playing, but anyway, they do work as actuators and they're very soft, and they have an alternative benefit that if we keep the unreacted photochemistry on the inside of the actuator and it gets pierced and leaks, then the sunlight can cure it and self-heal it. So using 3D printing, we do like haptic interactions as a way to demonstrate the value of it. We printed, this is using the carbon M1's elastomeric polyurethane, a handle that we could stiffen. It's got a lot of internal lattice work that allows it to keep its shape when it's inflating, but still be stiff. Then what Ben just did there is he squeezed on the handle to send a barometric trigger that started deflating the handle, and then he pressed that metal button, which changed the sword from a steel sword into a foam sword. And when it's in this configuration, you can't pop balloons, and it feels just like foam. So unlike the abstract representation of haptics before, this is a direct representation of it. Okay, so everything I've showed you has been a machine, not a robot. That's because controlling these things is very difficult without sensing, and in my opinion, we'll need sensing, and the more sensors we have, the easier it will be to control. So instead of using electrons and making stretchable capacitors and stretchable resistors, which are very good, we wanted to use photons so that we can have other valuable aspects like more data transfer. If you can use multiple frequencies simultaneously, and also if we like optical sensing, because we're making wearables out of this stuff that you can put in the washing machine and it behaves the same way. So what this diagram is a light guide that as you stretch it, the path length increases and the absorption goes up. So through Beer's law, you decrease the power output on one side. Some other work was done actually before us by Yonglei Park, where he coated a rubber light guide with some gold, and as he stretched it, the gold would crack and light would leak that way. It also probably uses this concept of Beer's law, but what I'm going to show you after this video is we remove the cladding altogether. So this video shows light into this light guide and being output on the other side. And when we stretch it, you get a linear decrease in the power output, which is good. In strain, it's a linear response. In this, we can cycle this a lot. We haven't noticed any failure in our cyclic loading tests. or change. We put these light guides into these prosthetic hands. This has 3 light guides you can feel in the fingertip, and when you pressurize the actuators, you can use the light guides to detect bending and also internal pressure. But what really we were just doing here was in this demonstration where we can feel these tomatoes is measuring the deflection of the fingertips as they go over it, and then the fingertip force versus deflection as we press into the tomato. We didn't really use the internal pressure measurement for this. Then we'll go by and we'll press on each tomato, and then effectively the stress strain curve will tell us which tomato is the most compliant and thereby the most ripe. Now, obviously, a visual approach would be even easier. You just put a camera on the end and it looks at the red one, and the one that's the most red is the most ripe. But we think that vision and touch should be used in combination, just like we do. So we've started to integrate visual processing as well as touch processing, but I don't have that in this talk. So those and I think I have 3 minutes left. Please correct me if I'm wrong. So those stretchable light guide sensors can't localize position of touch. By removing the cladding on that light guide and touching 2 light guides together, we can couple light at the location they touch using frustrated total internal reflection. And that will tell us where the deformation is happening as well as how much deformation is happening. This little video at the bottom and this cartoon at the top shows how we use that. We're just transmitting light from one light guide into another light guide. And then we thread these light guides into some printed lattice work to create volumetric displacement measurements in these deforming structures. Okay, by threading them into this cylinder, we get 12 different interfaces, all telling us how much they're pressed together to get this accurate cylinder reconstruction. Patricia Hsu, who worked on this, used an empirical model, but Ilse van Meerbeek used a similar optical sensing system. It's actually quite different, but for the sake of time, she uses optical sensing system and then neural networks to train a computer to infer the shape of the soft actuator. And it works pretty well, but it took around 2,000 training points. But, you know, I'm not a machine learning expert, but I think that's pretty good for what we got. Okay. The last optical sensing technique I'll show you is where we actually color the light guide. So depending on the color that comes out of the end of 2 cores, we can say where the deformation is happening and, you know, the mix of colors. So I'll just skip to the end here and show that we can get simultaneous position reconstruction. And in a minute, Lilia will press on her finger to get force measurement as well. So that knuckle is lighting up. And that's because we can use color and intensity information and decouple them to get position and stress. So my group is really great. Very lucky to have them all. Most of this work was done actually by Cameron Oben and James Peekle, who aren't in here. Ilse van Meerbeek, she's at Lawrence Livermore now. And then Patricia Hsu, she's still in my group. And Kaiyang Wang for the 3D printing. So, you know, if you could actually hear what I was saying, I'll happy to take any questions, and thanks for dealing with me doing this remotely.